In this video, we're going to be looking at topic 13A, chemical equilibria, and we're going to be focusing on the first part of the topic, specifically looking at Kp and Kc, and this is part of the International A-Level Chemistry course from Edexcel. So we're going to be looking at how we deduce expressions for Kc in terms of the equilibrium concentrations. We will also look at Kp in terms of the equilibrium partial pressures, and how we can then calculate the units for this as well. So first of all, we need to understand what the difference is between a homogeneous and a heterogeneous reaction. We're going to start off by looking at the homogeneous reaction. So this means that all of your reactants and products are in the same phase, i.e. they are all gases, they are all liquids, or they are all aqueous. In topic 9 in year 12 or AS level chemistry, you looked at how the position of equilibrium can be affected by factors such as pressure, temperature, and concentration. What we do now in this topic is we look at how to quantify that. So we actually now put a number onto the position of equilibrium, and based on that number we can make a prediction about where the position of equilibrium sits and then how changing these factors changes that position. So rather than just being qualitative, now we're looking at the actual number, and we will go into the factors of how they affect equilibrium in the second part of this topic. So what we know is that all reversible reactions can reach dynamic equilibrium. And again, we covered this back in topic 9, where we see that the forward and the backwards rate of reactions are the same. So the forward reaction is happening at the same rate as the backwards reaction, and this causes your concentrations of your reactants and products to remain constant. And of course, your reaction is continuous, so both your forward reaction and your reverse reaction are happening at the same time. Note that the rates are equal, but the concentrations are constant. They do not necessarily have to be equal, so it's important that you get that distinction the correct way around. So what we can now do is we can look at a specific reversible reaction. So here we have one molecule of N2O4 as a gas decomposing into 2 molecules of NO2 as a gas. So what we can do is we can now apply equilibrium law in order to calculate this equilibrium constant. And this happens at a particular temperature. And what we do is we relate the concentrations of the products, and we use the coefficient of 2 as your index, and we relate that to the concentration of the reactants. So your products are at the top, your reactants are at the bottom, and we use square brackets to show that these are specifically concentrations. You cannot use round brackets. They are very, very clear on this, and you will see why when we look at Kp. So the subscript C in Kc is used to show that we're calculating this in concentrations, and sometimes you might have a subscript here of Eq to show that these concentrations are those at equilibrium. However, the exams do not necessarily always ask for those subscripts because it is implied by calculating Kc that these are the equilibrium concentrations. So the most important part is that you get the substance and the products and the reactants, the state symbol, and the index correct. Now, at a given temperature, Kc does not change with the concentration. Now, this is different to the position of the equilibrium. So what we're saying is this value is constant. The only factor that affects it is temperature. And so Kc is different to the position of equilibrium. Please bear that in mind, and again, that's something that we'll talk more about later on in the second half of this unit. So there are 2 ways that we can determine Kc. We can do it either through experimentation, or we can use calculations using thermodynamic equations. And if we have this general reaction here, we can write out a Kc expression. So it is the concentration of our reactants to the power of their coefficients. So in this case, the concentration of C to the power Y times D to the power Z over the concentration of A to the power W multiplied by the concentration of B to the power X. That is how we calculate Kc, and it will always depend on, of course, what reactants and products you have in your specific reaction. This is just in general how we write out the expression. Now, similar to our rate constant that we met back in topic 11, our units of Kc can change, and it all depends on the equation. So we should know that the units of concentration are moles per decimeter cubed. So to calculate the concentration of Kc, to calculate the units of Kc, we have to take into account how many moles per decimeter cubed we are multiplying. So in this case, for my Kc, if my concentration is squared, I have moles per dm cubed times moles per dm cubed. If I then go to the bottom half, I have the concentration of the hydrogen is cubed, so I have to have that 3 times, and then I am then multiplying it by the concentration of the nitrogen, so that is also included. So I now have 4 moles per dm cubed at the bottom. My top can cancel out, and that leaves me with Kc is equal to 1 over mole per dm cubed times mole per dm cubed, which would be moles squared dm to the minus 6. But because that is 1 over, Kc ends up as moles to the minus 2 dm to the 6. Or, best practice is to put the positive in this first. So it's dm to the 6 moles to the minus 2. Whereas our other expression, Kc is equal to the square of Hi, so that is twice, over the concentration of the hydrogen times the concentration of the iodine. So Kc, therefore, these will all cancel out, and this case has no units. This is a very common multiple choice question, so they will regularly ask this in order to figure out the units for a Kc expression. And when you actually do the calculation, 9 times out of 10 you will also get a mark for the units as well. So it is very important that you are able to do this. You might want to practice it for a number of different expressions, or you can practice it as you're doing your past paper questions. But it is very, very important to be able to do. Now, to determine the value of Kc, we take known amounts of the reactants, we put them into a sealed container, and we allow them to reach equilibrium with their products. Once we are at the point of equilibrium, we determine the amount of one of the substances in the mixture, which is typically one of the products and usually done by titration. But there are other methods depending on what it is that you're measuring. And then once we have that one substance, we determine the concentration of everything else using the stoichiometric equation. And the way that we do this is we look at how the moles of reactants and the products have changed. So for the reactants, we take the initial moles and we subtract the amount of moles that have reacted. And for the moles of the product, we start with the initial moles, and this time we add the moles that are formed. Now this can be quite tricky, so what we can do is we can use a specific method. The method that we would use to calculate Kc is known as the Rice method. So for a general reaction that we've been looking at, so Wa plus Xb is an equilibrium with Yc and Zd, we can use this Rice method, which is known to stand for reaction, initial, change, and equilibrium. So we have our reaction or our reactants and our products. We know what our initial moles are. We look at what the change in our number of moles is, and then we determine what the number of moles is at equilibrium. So for example, if I have a concentration of one of the products at equilibrium as Q, in order for me to get my change, I take that Q and I multiply it by the coefficient, because of course we have to take into account that the coefficient is applying a ratio. So if we have a 1:2 ratio between two substances, we have to take that into account of how much is going to be used. So for our reactants, our reactant A, we would be subtracting W times the concentration Q. For B, it would be X times the concentration of Q that would be subtracted. For C, because C is a product, we would be adding Y times Q. And for D, we would be adding Z times Q. And this, remember, is to then be from the initial moles, and this gives us our number of moles at equilibrium. Now, the best thing that we can do for these is to actually look at a specific example. So we have got 2 moles of ethanoic acid and 2 moles of ethanol being mixed in a closed container and allowed to reach equilibrium with ethyl ethanoate and water at 298 Kelvin. The amount of ethanoic acid at equilibrium is found to be 0.67 moles. Calculate Kc. So you would likely be given the balanced chemical equation for this, or you may be asked to work it out because this reaction does form part of topic 15, but 9 times out of 10 you will be given the reaction here. And what we find is that all of our reactants and products are all in a 1-to-1 ratio. So we have our ethanoic acid, we have our ethanol, we have the ester, ethyl ethanoate, and then we have our water. So our initial concentrations, our initial number of moles, is 2 for the ethanoic acid and 2 for the ethanol. Now, of course, we must have 0 and 0 for the ethyl ethanoate and the water, because at the very start of the reaction, we haven't made any. When we then have to look at our change, we are told that the amount of ethanoic acid at equilibrium was found to be 0.67. So my equilibrium here is 0.67. This means that my ethanoic acid has come down by 0.133. So that's my change. So I've said my initial is 2, it is changing by going down by 1.33 to give my equilibrium moles as 0.67. Now, because these are all in a 1-to-1 ratio, each of them does the same thing. So this comes down to 0.67. For my products, I'm adding the 1.33. So now I have my number of moles of equilibrium. I can then convert these into concentrations. And the way to convert them into concentrations is to divide by the volume. Now, in this case, we are not told a volume, so we will just simply denote the volume as the letter V. So this, for my concentration, would become 0.67 over V, 0.67 over V again, and my 2 products would be 1.33 over V. Now, it doesn't matter that we don't have the value of V because these are going to cancel out when I get to my expression. So for my Kc expression, it is the concentration of the ethyl ethanoate, and I'm just going to shorten that for the sake of this question, times the concentration of the water, all over the concentration of the ethanol, times the concentration of the ethanoic acid. Therefore, Kc is 1.33 over V times 1.33 over V, all divided by 0.67 over V times 0.67 over V. And now you can see that the volumes are going to cancel each other out. So they're going to have no major effect on this. And once I put all of this into my calculator, I find that my Kc value is 3.94. And my units are also going to be cancelled out because I have moles per dm cubed times moles per dm cubed at the top as well as at the bottom. So my final answer is simply 3.94. And you could write no units if you wanted to. But in an exam, if you do not include units, the implication is that there are none. If we look at a second question, so we have 0.1 moles of N2O4 being placed into a 0.1 decimeters cubed flask, so this time we are told a volume, and allowed to reach equilibrium with NO2 at 398 Kelvin. And at equilibrium, there is 0.071 moles of N2O4. Calculate Kc at this temperature. Now, we've already seen this expression, or this equation, because it was in our previous slides, but just a reminder, this was N2O4 gas decomposing into 2 NO2. And this time we have a coefficient, so we have to be aware of this. So I have my N2O4 and my 2 NO2. And I'm going to write the coefficient into my table just so that I remember. So for my initial moles, I'm told I have 0.1. And of course, I haven't made any of my products. So again, this is 0. I'm told that my number of moles of the N2O4 at equilibrium is 0.071. So therefore, my change must be 0.029. And this is coming down by that. My N2O4 must be going up by 0.029, but because I have that coefficient of 2, it is actually going up by 0.029 times 2. And that gives me a value of 0.058. So now I have my number of moles, I can work out my concentration of both of these substances. So my concentrations will be 0.071 divided by the volume of 0.1. And again, 0.058 divided by the 0.1. So now I have my Kc expression. So my Kc expression is the concentration of the NO2, which is squared because of the coefficient, over the concentration of the N2O4, which has no power. So now my Kc is going to be 0.58, because that's what we will calculate our concentration to be, and we square that, over 0.71, and Kc is therefore 0.474. And for my units, I have moles per decimeter cubed times moles per decimeter cubed at the top. And at the bottom, I have 1 moles per decimeter cubed. So one set will cancel out, and it leaves me with a units of moles per dm cubed. And that is my answer for Kc. So for our third and final example for Kc, we are going to look at the reaction between nitrogen and hydrogen to form ammonia. So looking at our equation, we can see that we have N2, we have 3H2 and 2NH3. And I'm told some information in the question, of course. So I'm told my initial moles of N2 is 1.5, and I'm told my initial moles of the hydrogen is 4. I'm also told that it's in a 1.5 decimeter cube container, which will be important later, and at equilibrium, 30% of the nitrogen has reacted. So if I take my 30% of 1.5, that gives me a value of 0.45. So my nitrogen is coming down by 0.45, which will bring that number of moles at equilibrium down to 0.105. Okay, so to get my change, I simply did 1.5 times 30%, which is 0.45. My number of moles of initial of the ammonia is of course 0, and that must be going up by the 0.45 times the coefficient of 2, which would bring you up to 0.9. For the hydrogen, it is coming down by 0.45 times the coefficient of 3, which will bring your equilibrium moles to 2.65. I can of course work out the concentrations by looking at my volume of 1.5, so I divide each of these by 1.5. Now you can show this as an additional step, or you can write it directly into your Kc expression. It's completely your decision. So in this case, I'm going to write it into the Kc expression so that we can see what this looks like. So I have the concentration of the ammonia to the power of 2, because it has that coefficient of 2. I have the concentration of the nitrogen at the bottom times the concentration of the hydrogen, which is to the power of 3. So my Kc is going to be 0.9 divided by the volume of 1.5, and that is going to be all squared, over the 2.65 divided by 1.5 for the hydrogen, which is cubed, times the 1.05 over 1.5, and there is no index for that. So when you put all of that into your calculator, you find that Kc is 0.0927, and you would work out your units in the way that we have each time, and you get moles to the -2, decimeters to the 6. And that would be your final answer. So there are 3 very similar questions, just taking into account the coefficients and being aware of sometimes they can ask the equilibrium concentrations in a slightly different way, in this case using percentages. Now, if we have a heterogeneous reaction, this is one in where the reactants and products are in different phases. So if, for example, we've got calcium carbonate, which is a solid, giving you the calcium oxide and the CO2 as a gas, we again apply our equilibrium law, so the concentrations of the products over the concentrations of reactants are equal to a constant, or Kc. The main difference here is that the concentration of a solid is determined by its density for a specific temperature. Therefore, these are constant values. So these concentrations are not going to change. So we take them out of our equilibrium expression, and in this case, we are only left with CO2 as the gas. So our Kc expression is this one at the bottom. Kc is equal to the concentration of the CO2 as a gas. So be aware, if you do have solids in your equation, they should not be present in your equilibrium expression because they are determined by their density, and that has a constant value. The second equilibrium constant that we have to look at is known as Kp, and this is for reactions that involve gases. So rather than looking at them in terms of their concentrations, we can express the equilibrium constant in terms of something known as their partial pressures. And what does this mean? Well, a partial pressure of an individual gas in a mixture is defined as the pressure the gas would exert if it alone occupied the volume. So we're taking into account the fact that we have this mixture of gases, and we're trying to figure out for each of the gases what pressure would they have if they were on their own. And the way that we do this to find our total pressure is the sum of all of our partial pressures. So we can now relate the total pressure into the pressures of the gases that make up the mixture. So for a mixture of gases A and B, we say that the total pressure, P, is determined by the partial pressure of A plus the partial pressure of B. So we're going to get a slight difference in how we calculate these reactions and how we carry them out, but the way that we write out the equilibrium constant is very similar. So what we've seen for Kc is that we used square brackets to show that these contain concentrations. For Kp, we should be using round brackets, and we have to have the P there as well to show that it is a pressure. Now, sometimes you may see the P outside of the brackets, or you may see the P inside of the brackets. Both of them are accepted. So in this case, we're going to write this round brackets P and then C, so the pressure of C to the power of Y, times the pressure of D to the power of Z, over the pressure of A to the power of W, times the pressure of B to the power X. So our coefficients are still being used as our indices. Our reactants and our products are still being used in the same way, where the products are at the top and the reactants are at the bottom. The main difference here is we're moving away from the square brackets and we're putting the round brackets and the P. This may sound very specific and it may be annoying to have to remember this. However, they will not give you marks in an exam if you write Kp with square brackets. They are very particular about this, so please make sure that you check and you read the question carefully to determine is it Kp or Kc. Another reason why we have to be aware of whether it's KP or KC is because KP requires some additional steps, and it requires the additional steps of actually calculating these partial pressures. So the partial pressure of an individual gas is calculated by multiplying the mole fraction by the total pressure, i.e. of your total moles, how much of it is a specific gas, and then we multiply that by the pressure. So our mole fraction requires us to calculate the total number of moles at equilibrium, and then we put the number of moles of our reactant or product over that total number, and then we multiply it by our total pressure to get the partial pressure. Again, for reactions that contain solids, we ignore the partial pressures because they would not have any effect, and we don't put them into the equilibrium expression. So we're only including gases in a KP expression. So of course we want to put this into practice because that's the best way that we learn. So we have got this particular reaction. We have 1 mole of PCl5 vapour being heated to 500 Kelvin in a sealed vessel, and the equilibrium mixture at a pressure of 6 atmospheres contains 0.6 moles of Cl2. And we want to calculate Kp. So we're going to put in our PCl5, our PCl3, and our Cl2. Okay, all of them in a 1-to-1 ratio. We're told that our number of moles at the start for the PCl5 is 1, and of course our products are 0. We then find in the equilibrium mixture that our number of moles of the chlorine is 0.60. So my change here is to go up by 0.60. So that must mean that the PCl3 does the same thing. And my PCl5, with it being a reactant, is going to come down by 0.60, giving you 0.40. Now, you may be wondering, why do we have the fourth column? Well, we're going to have this in because we need to figure out our total number of moles. So we add 0.4 plus 0.6 plus 0.6, and that gives me 1.6. And now I can determine my mole fraction. So my mole fraction would be 0.4 over 1.6, the 0.6 over 1.6, and again the same for the chlorine. And these give you values of 0.025 and 0.375. I'm told that my total pressure is 6, so now I take my mole fraction and I multiply it by my partial pressure. And again, you can do this as a specific step in the table to get the value, or you can take that and substitute it straight in to your partial pressure, so your Kp expression. So I'm going to put 0.25 times 6, 0.375 times 6, and 0.375 times 6 again. So in this case, our Kp expression is the partial pressure of PCl3 times the partial pressure of Cl2 over the partial pressure of PCl5. So I'm going to substitute in those numbers. So I had 0.375 times 6 times 0.375 times 6 over my reactants, which was 0.25 times 6. And again, I can put all of that into my calculator and I find my answer to be 3.38. And this time my units are not moles per decimeter cubed because they are gases, and because we're measuring our partial pressures in atmospheres, we are going to have atmospheres as our unit. So the way I would have this is I would have the top being atmospheres times atmospheres over atmospheres. 2 of them would cancel out, so it leaves you with an overall unit of 3.38 atmospheres. And that's how we calculate the Kp expression for this particular substance. If we look at a second example to give us a bit more of detail. This time, again, we have the Haber process. So we previously seen this as a Kc expression. Now we want to look at it as a Kp expression. So I'm going to have my N2, my 3H2, and my 2NH3, and we know this last one is going to be our totals that we need. So I'm told that I have 1 mole and 3 moles of the H2, and for my NH3, that has to be 0. At equilibrium, I'm told that 20% of the N2 has reacted. So if I take my 1 and I do my 0.2 or my 20%, that gives me a value of 0.2. So my change is to come down by 0.2, so my equilibrium moles for nitrogen is 0.8. For my hydrogen, that is going to come down by 0.2 times 3, because remember there is that coefficient of 3, which would bring my equilibrium moles to 2.4. The ammonia must be going up by 0.2, and I multiply it by the coefficient of 2. So that gives me 0.4 moles at equilibrium. Again, I have to calculate my total number of moles, my total number being 3.6. I can then do my mole fractions. So I have 0.8 over 3.6, which is equal to 0.222. I have 2.4 over 3.6, and that's 0.667. And the 0.4 divided by the total moles, which gives you 0.111. I'm told in the question that I have a total pressure of 2 atmospheres. So to work out my partial pressure, I do my moles times my partial pressure. So I have 0.222 times 2, 0.667 times 2, and 0.111 times 2. Now again, I show my Kp expression. It's very important for you to actually write out the Kp and Kc expression so that you can make sure that you get those marks, because they are generally given 1 mark. So we have the partial pressure of the ammonia, and that's to the power of 2, over the partial pressure of the nitrogen, times the partial pressure of the hydrogen, and we cube that. So Kp is therefore equal to 0.111 times 2 squared over the 0.222 times 2 multiplied by 0.667 times 2, and then we cube that value. Kp therefore is going to be 0.0469, and using the same method of units that we've previously used, only this time we're using atmospheres, you work your units out to be atmospheres to the minus 2. And that is your final answer for the Kp expression in this case. So as with our other videos, let's finish off with some past paper questions. So firstly, we're given the reaction between P and Q in the equilibrium of R, and we want to figure out the units of the Kp constant. So because it's Kp, it's going to be measured in atmospheres, and remember it is products over reactants. So in this case we have 8R, so that would give us 1, 2, 3, 4, 5, 6, 7, 8, and I'm just writing A to stand in for atmospheres in terms of quickness. You can do this in the exam because they're not going to be checking that working, they're only checking your final answer. And then that's all going to be over the 1A from the P times the 3 from the Q. So that's going to cancel out 1 and 1, 2 and 2, 3 and 3, 4 and 4. So that is then going to give me the atmospheres at the top, and there are 4 of them, so the answer must be C, atmospheres to the power of 4. Remember, if it was atmospheres to the negative 4, the 4 that are left over would have to be at the bottom, so it would be 1 over atmospheres times atmospheres times atmospheres times atmospheres. For the second one, when magnesium hydroxide dissolves in water, the following equilibrium is established. Therefore, the expression for the equilibrium constant Kc is what? So very important here that we look at the state symbols. We can see that we've got aqueous state symbols in our products, but for our reactants, it is a solid. And remember, solids should not appear in your equilibrium constant, so we can automatically get rid of C and D. And we have to look at then our coefficients, and because the OH has a coefficient of 2, it becomes the indus, so your answer must be B. It is Mg2 plus aqueous concentration times the OH minus aqueous to the power of 2. We now have this reversible reaction below, so this is our usual one that we've seen multiple times now. So the dinitrogen tetroxide, or N2O4, being in equilibrium with 2 moles of NO2, or nitrogen dioxide. And a chemist investigating this reaction started with 5 moles of the N2O4. So my initial was 5. And for the NO2, of course it is 0, and it tells us that 2 moles of that forms. So that must be plus 2. Because they're in a 2-to-1 ratio, this is going to be minus the 2 divided by 2, so really it is minus 1. So my moles at equilibrium for the N2O4 is going to be D, 4 moles. So that's just using your Rice table as your shortened version. Under different conditions, 25% moles of the gas present is N2O4. If the total pressure of the system is 3 atmospheres, what is the numerical value of Kp? Now, by giving you the 25%, what they've actually done is they have given you the mole fraction. So remember, the mole fraction is then used to work out your partial pressures. So in this case, Kp is going to be the partial pressure of NO2 squared over the partial pressure of the N2O4. So our partial pressures here are going to be 25% for the N2O4. So 25% times the pressure of 3. And then on the top, that must be the remaining 75% times the pressure of 3, but that will be squared. And that is going to give you an answer of 6.75. So your answer is B. Now we're going to look at more written questions. So methanol can be synthesized by the reaction of carbon monoxide with hydrogen. And in a mixture, we have 18.5 moles of carbon monoxide, 13.5 of hydrogen, and it's at 550 Kelvin and 60 atmospheres. And the equilibrium mixture contained 5.5 moles of methanol. First of all, write a Kp expression for this reaction. So Kp is going to be equal to the partial pressure of the C3OH over the partial pressure of the CO multiplied by the partial pressure of the H2, and that has to be squared because it is a coefficient of 2. Now we want to calculate the number of moles of the carbon monoxide and hydrogen remaining at equilibrium, and therefore calculate the value of Kp at 550. And we want to give our answer to 3 significant figures and include the units, and this is a nice 5-mark question. So the first thing we're going to do is we have our Rice table, and then because it's a Kp, we are going to calculate the mole fraction, and then we will calculate our partial pressures. So let's draw this out. I would strongly recommend doing this in your exam as well, because it shows the examiner all of the different parts of the calculation and it allows them to follow through where you got your marks. So we know that we're going to have, if we go back to our equation, the CO, 2 H2s and the CH3OH. So carbon monoxide, 2 H2 and the methanol. We're told that we start with 18.5 of carbon monoxide and 13.5 of hydrogen. So 18.5 and 13.5. And of course our methanol is 0. Going back to the question, it tells us that we contain 5.5 moles of methanol at equilibrium. So if this is 5.5 my my change here is plus 5.5. So now I look at my reactants. Well, if my products are going up by 5.5, this must be coming down by 5.5. So my equilibrium moles is 13. And for my hydrogen, it is coming down by 2 times 5.5 because there's that coefficient. So it's coming down by 11 to give us equilibrium of 2.5. Now my total number of moles, which I need for my mole fraction, is 21. Now I put in my mole fraction as 13 over 21, which is 0.619. 2.5 over 21, which is 0.119, and 5.5 over 21, which is 0.262. Again, if I go back to my question, I'm told that I have pressure of 60 atmospheres. So this is 0.619 times 60, which gives you an answer of 37.14. 0.119 times 60, which gives you 7.14, and 0.262 times 60, which gives you 15.72. Now we put all of that into our KP expression. So we have 15.72 for the methanol over the 37.14 multiplied by the 7.14 for the hydrogen, and remember that is squared, and Kp therefore equals 8.30 times 10 to the minus 3. And for my units, I'm going to have atmospheres at the top over atmospheres times atmospheres times atmospheres. These two cancel out, so it becomes 1 over atmospheres times atmospheres. So my units are atmospheres to the minus 2. That is 5 marks for that question. You get first mark for figuring out your number of moles at equilibrium of your CO and your H2. You get your second mark for calculating your partial pressures. You get your third mark for putting your answers into your partial pressures into your Kp expression correctly. Your fourth mark for the answer to 3 significant figures, and the fifth mark for your units. Our last question is going to look at a KC past paper question. So we have hydrogen cyanide and propanone and ethanol reacting to form cyanohydrin, and we get this equilibrium. Now this one's a little bit different in the fact that we are given the volumes and concentrations. So we can either calculate the number of moles, or we can use our Rice table using our concentrations, and that's the way that I'm going to do it. But I will show you the past paper mark scheme that shows you the second method. So we're told that we have 100 centimetres cubed of 0.1 moles per dm cubed propanone, and we mix that with 100 centimetres cubed of 0.2 moles per dm of the hydrogen cyanide. And the equilibrium concentration of our product is 0.034. And for 4 marks, we're calculating Kc, and we give our answers to 2 significant figures. And of course, including our units. So again, I'm going to put my Rice table, because I want to show the examiner all of the knowledge and I know where each of these is coming from. So I have my propanone, I have my HCN, and then I have my cyanohydrin. So I'm told that my concentrations this time that I'm going to use are 0.1, 0.2, and of course that their product has to be 0. And at equilibrium, I'm told this is 0.034. So my change here is plus 0.034. Now because they're all in a 1-to-1 ratio, my changes are minus 0.034. So that now gives me new concentrations at equilibrium of 0.066 and 0.016. Now I put my Kc expression, so it is my reactants, so my products at the top. And remember my square brackets over my reactants. And now it's just a case of substituting in my answers. So I have 0.034 over 0.066 times 0.016. And that gives me an answer of 32.19, which I need to put into two significant figures. So my answer is 32, and my units are going to be mole per dm at the top, cancels out 1 at the bottom. So it would be moles to the minus 1 dm cubed. But remember, best practice is to put the positive index first. So it would be dm cubed moles to the minus 1. So there's the mark scheme for the first set of questions, including our KP expression if you were trying that out. So notice that we can have our marks being broken down, and it's very specific that we have to reject square brackets. And for the second past paper question, we used method number 2, but as I mentioned, you can use our number of moles to figure out our using our different method, or looking at the difference in terms of just the way that we lay it out. That's everything for part 1 of topic 13, chemical equilibria. Part 2 will cover the effects on Kp and Kc of changing our pressure, concentration and our temperature. If you do have any questions, please feel free to leave a comment below, and we hope to see you back soon.